Hello everyone, what is up? Today I am going to talk about a very controversial opinion actually. Uh, I am going to say that computer science is no more about computers. It is applied mathematics. It has always been applied mathematics. If you have been thinking that computer science is about computers, it is about making apps and all that, you are wrong. You are wrong. You should, if you don't agree with me, if you think that I am misguiding you, or if I am not telling you the truth, you can already click off of this video. Computer science is not about computers. It is about applying mathematics. Now, why do I think that? Let's uh, see how we actually program nowadays. Nowadays we have, a lot of uh, practical programming languages, I would say. Languages like Python, languages like JavaScript or even Rust. These languages are mostly imperative in nature, but nowadays these languages also have something called functional patterns, uh, ho- things that are also called higher order functions, which you can see in the form of map, filter, flat map, fold. I don't know if fold is present in Python or not, but fold is present in Rust. Fold, we have zip, we have some product, collect, and all these higher order functions. So the thing that I am getting to is, if you go down the functional rabbit hole, you will see that computer science is not actually about computers. And you would ask me, why do I have to go functional to see this? Because uh, let's see, let me think of some sort of algorithms. Okay, all of us know what merge sort is. Merge sort is a general purpose recursion based algorithm that is used to sort arrays. It is a very elegant algorithm. I believe it is a very elegant algorithm, and when you implement it iteratively or imperatively in any of these commonly used languages like C++, Java, Rust, Python, JavaScript, what we do is we tell the computer or the machine that is going to implement the algorithm. Again, computer science is I computer science is not about computers. It is about computation. Computation can be done by any kind of machine. It can be done by a machine, it can be done by a human, it can be done by anything. So whenever we are describing an algorithm, there are ways in which we can describe an algorithm. Commonly, or in most languages, we describe it using something called an imperative approach. We tell it how to do that sorting, or how the sorting is done. We tell it that, okay, go ahead and divide this array, keep dividing the array until we reach atomic size. After reaching atomic size, start merging those arrays back, and finally we will have a sorted array. We are going to use some extra space and all of that good stuff. But if you start using functional programming language or purely functional programming languages like Haskell, you will see that when you start, you know declaring, or you cannot call it how the algorithm works. The best way to describe how you write functional code is, this fly is getting in my face. How you write functional code is, you don't tell the computer or the machine that is going to compute how it has to do something. You tell it what it actually is, what the algorithm actually is. You tell it what its base cases are, what is being done inside the algorithm. You are not telling it how it is being done. And now you would ask me, how is it superior than telling it how it has to be done? uh, let's talk about traditional for loops. There is nothing wrong with the traditional for loops. There is nothing wrong with mutable states in any kind of function. But in traditional for loops, in languages like C++, there is a tendency to create problems that can be avoided simply if you use functional patterns. For example, let me give you an example. Suppose we are taking each number and just squaring it. We can use our functional pattern to iterate over that data, map it, use a closure to say that we have to, for whatever value x is, we have to x times x, that is x squared, and just collect it. Now, it is not, you cannot mess that up. But for in traditional for loops, you can, for a very naive example, you can index over the wrong ranges. You can go from 0 to, let's say, the size of the array is n, but what if you uh, were using an inclusive range? You go out of bounds. So these types of issues are really prevalent in traditional iterative approaches. But functional approaches, in functional approaches, it is easier to debug. You can basically see, okay, the transformation that you are going to do on this data is basically defined by this closure. There are no global mutable states, and everything is pure. Now what, if you start going down the functional rabbit hole, you will eventually come across something called a pure function. Now what a pure function actually is: suppose we have something global, we have some global variable x. When you first pass it into an impure function, it creates an output y. When we pass x, it creates an output y. When we again pass x into it, it is not it in an impure function, it does not guarantees that x is going to create the same output y. But a pure function guarantees that provided x is same, you will always get the same output y. This again this is something like when Dr. Octopus said, the power of sun in the palm of my hand. When unless you are trying functional approaches, unless you are doing map, filter, collect on a daily basis, you would not understand how good those tools really are. If you are not, if I don't care what languages you are using, if you are using Python, if you are using JavaScript, most languages have functional patterns nowadays. I want you to click off of this video because I'm going to end it pretty soon. As soon as I cross the 7-minute mark, I'm going to end this video. As soon as this video ends, you have to go, you have to learn what functional patterns your languages offer. Whatever language you are working with is offering. Python offers map, filter, and I think it offers reduce too, but I mostly use map, filter. Rust is my goat. It has most of the functional patterns. But if you really want to get the functional juice inside of your brain, if you want to see where the ideas are coming from, you have to try Haskell. You have to try Haskell. But again, before you jump ship and start learning Haskell, I would say try these functional patterns in the whatever languages you are working with. I hope this video made some sense. And again, if you didn't learn anything from this video, you should remember that computer science is as less about computer. I don't exactly remember the quote, but it goes something like, computer science is as much as about computers as much as astronomy is about telescopes. I don't know who said this. I think Dijkstra said that. uh, I don't really care whoever said that, but you have to remember this, and you have to remember that computer science is applied mathematics. You have to treat it with respect. You have to see it as mathematics, not as I'm going to go to my computer to prompt an AI and use the code. Use the code, but see what the program is truly doing. Good luck.